So, good afternoon all. My name is Raffaele Malvermi. I have to admit, just before starting, that this is my first talk as a PhD student, so I hope this will be enough clear or enough satisfying for us and for you. And the idea is to present the remaining works that we are following here at the Musical Acoustic Lab in Cremona, with a focus in using data-driven techniques, again, still, in some problems related to violin making. And the context that I think is more related to this kind of problems with respect to the one presented by my colleagues is that in vibration characterization, if we want to have a full description, if we want a fast description, I think that the previous talks have in a very clever way explained everything. So and I'm quite honored to have followed the talks. But if we want a full description of the body, we need, for example, of a musical instrument, we need to measure a lot of points and to make measurements that, for example, in the extreme cases of the violins that are here in the museum cannot be used. For example, we cannot attach accelerometers to the body of instruments, and also we cannot make several measurements. We need to use one accelerometer at a time and change the point and then make the test, so it's quite time consuming. And as it was said during the introduction of the laboratory, we have an alternative solution, which is using, for example, laser vibrometers. But since our tradition in the lab is more related to signal processing and space-time signal processing, we have a lot of microphones, but very bad laser vibrometers. So the idea is to try to propose solution with what we have up to now. So starting from acoustic measurements of instruments. Then another problem, I think, is also talking with luthiers, the idea of making a lot of measurements to have an overall description of the vibrational characteristics of musical instruments. And also the idea that, yeah, I'm quite embarrassed because we have just followed this morning a talk which solve, I think, the problem of expensive equipment. So I don't think I need to talk too much about that, but we need to find ways to, clever ways to use inexpensive equipment and try to clean up signals, try to have good estimations. And if we want to have something which is not only an hint of the mode shapes that we are trying to see, we need to perform many measurements, and still we don't have the overall idea. So we need methods to try to generate coherent data from the ones that we have, so from a few set of measurements. And I think these three targets are the ones that are leading this research solution that we are trying to study, which is finding a contactless method for vibration analysis, which starts from acoustic measurements. And here the idea is to find a way to use Neophyte acoustic holography, also in the case of violin plates. The idea of reducing the number of acquisition is finding a good way to make interpolation from the data that we have. And then third, which is a more applicative project, is the Bellakit project, which is a way to enhance the quality of estimates also when we have cheap equipment. So starting from Neophyte acoustic holography, which I think is very theoretical, so I want to give a very short intuition about what it is. The idea is that we are able to describe in a very effective way the forward acoustic propagation. I mean, we know that due to an excitation, a musical instrument, a vibrating structure can vibrate, and this vibration can be described by its modes of vibration. Then there is the coupling with air, which has to be included. And the vibration makes the air vibrating and generates sound pressure waves. And then a receiver, which can be a listener in the auditorium, or in the lab, we can use a microphone array, is able to acquire the sound field. So if we try to put all the theory that we know and all the models that are working up to now inside all these steps, we can defining an operator F, which includes everything. The idea of near-field acoustic holography is to find the inverse operator, F-1. So we have the sensors acquiring acoustic signals, and we want to find the description of vibrational behavior of our source. The problem is that here we are dealing with a mathematical problem. Every time we try to invert something, we have impulseness. So we are not sure that we have a unique solution. We have many solutions. We try to find a way to find the best solution between the infinite available, and also for the particular characteristic of the problem. In this case, near-field acoustic holography is one method which is very sensitive to noise. And noise can be inside the equipment that we use for measurements, and also the positioning of the microphones can be a problem, because if we assume that the microphone are positioned in some places and then there is an error in this positioning, we can have a solution which is diverging from the expected one. So the idea is, okay, what we can use to find a way to regularize, this is the mathematical term, the problem. The literature showed that many solutions which were quite successful were able to find a good way to represent the data that you have. And this is why our intuition was to use a data-driven model. As Sebastian said in his talk, data-driven models are like black boxes. If you have data, and if you have enough data, you are able to learn every type of function, every type of predictor that you want. And this is the most canonical and classic example. You want an algorithm which is able to recognize dogs from cats if you use as an input an image of a dog. The black box says, if you give me enough data, enough examples to understand what is a dog and what is a cat, I can do it for you with a good accuracy. All the recent works in image processing techniques is done in this way and is beating the state of the art. So what we said is, why don't we try with our data? So the idea is, okay, how to give a data set to this black box? We can make finite element simulation. So we can use, for example, the mesh created by Sebastian, creating thousands of violins with different outlines and different arching shapes. And we made the structural mechanics simulation. We have the vibration, and then we can have also the radiation on a plane. And this is done by the operator F. That can be any numerical method that we know. For example, finite element methods, boundary element methods. But the idea is, okay, now that we have this data set, let the model learn using the sound pressure as an input and the vibration as an output, to try to approximate that F-1 that we are trying to search. We did it, and these are some examples of the results of the reconstruction that we found. Here you can see the pressure that we gave as input. On the second column, the prediction by the network, because we used a convolutional neural network. This is the name of the data-driven model that we chose. And we compare them with the simulation output with respect to the velocity field. And we use, again, a metric that you already seen in the other talks, which is the normalized cross correlation. So the idea is to understand if the pattern was predicted in an accurate way. And this is a number between 0 and 1. And you can see from the plot that from test examples, which are examples that are not seen by the network. So the network has to predict these examples by scratch. And the patterns show good accuracy in most of the cases. Also, we did other tests considering the values predicted by the network. If you look, for example, in the middle here, you can see that the middle area of the second prediction is not as the one expected. So there are slightly modification in the predicted values, which is a thing that we need to adjust, but the relative prediction error is quite low, about 2%. We tried this method and we tested just to understand if it was robust to conditions which are similar to experimental setup, because now we are only validating the method with simulated data. So we added noise, such as microphone noise. We try to take and export the data in different positions, randomly chosen, just to simulate the idea of mispositioning the microphones. We saw that the method was quite robust also in this case, but as you can see, the number of data and pixels that we try to export was very unfeasible in reality. So the idea is that we have validated the model and the model works, but we need to make it more related to reality, reducing the number of microphones that we want to use, and also trying experimental data on that. But we are quite confident on the effectiveness of the method, because the idea is to give enough data, I think. So the more data we can get and feed the network, the more accurate the result will be. Also, we tested the network with missing plates, so plates with outlines and arching shape, which were not seen during the training, and the network was able to understand them. And also we tried to make the network learn with lower modes and try to predict higher modes. And we saw that if the network knows the information about the first mode, is able also to understand data which is related to higher frequency modes, which is quite interesting, because the idea is that the network takes an input, tries to make some calculation and combinations of the data that you put in a non-linear way. And so there is a non-linear combination. We can say that there is the possibility that high frequency modes are a non-linear combination of the low modes, which is quite interesting, I think. If we want to reduce the problem and we have less measurements and we want an overall idea of the vibrational behavior, we need to find a way to generate new data from the ones that we know. And we use the same approach. So what we can know from a point on a violin plate is the frequency response function, as we saw. And the idea is, okay, let's take a subset of points on the violin plate. Let's put this, the magnitude of the frequency response inside a matrix that can be visualized as an image, and let's fill with all the points that we don't know. And again, using the same problem formulation and the same approach, we were able to find a satisfying reconstruction. Here you can see that on the right there is the predicted image, and the peaks and the resonances are reconstructed quite well. The only problem is the anti-resonances region, but this is a work which is going on, and we have tried different things, and now we are able also to reconstruct that. So the important thing here is that if we have big holes, that can be in reality the idea of having very less points known, or maybe trying to generate data in an area of our vibrating structure we are not able to measure something. For example, the fingerboard in a violin, or other shadowed areas of our instruments. So the idea is, okay, while we are using data-driven methods, the idea is that data itself contains information that we can try to explain and to use during our application. This is the first step. We want to use it in experimental data setups, and only in those we want to add what we know. So models, physical models, assumptions, which is not done still, but we want to do it. The other part is more an applicative part, which is the beta kit. The idea is to create a framework which is embedded and contains a set of functionalities that can be used by violin makers to do measurements and to have an estimation in real time of some vibrometric descriptors. And the name Beta Kit comes from the Beta platform, which is a real-time electrical circuit for audio acquisition, which is used mostly for interactions and creative projects. Here the idea is, okay, let's take this platform, use its ability to acquire signals in a very real-time fashion. Let's add some sensors and an hammer, which use the same sensor. And the idea is to create an open source application based with Python, where it is possible to have, for example, the estimation of the frequency response function. We can have the magnitude, the phase, and the coherence function for the frequency response function, as explained Tuesday morning. We can give some information about the resonances, where they are, the corresponding note, the magnitude, and the quality factor. And we can use it with different sensors simultaneously. So the channel 1, channel 2 are meaning the fact that we can use 1 accelerometers, 2, 3 accelerometers at the same time on the body. Also, the idea is to implement, we have implemented also model analysis on that. So we can take a measurement on a grid of points on our violin plate, and we are able to find the resonances and to give an idea of the mode shape for the body. And also, one thing which is more related to material characterization, and also Romain talked about that during his talk, is the idea of finding some mechanical parameters. In this case, we focused on the estimation of the longitudinal velocity of a tone wood. So the idea is to use the accelerometer that I showed you, 2 accelerometers with at the extremes of the tone wood, with a simple hammer impact. The idea is to find the velocity that best explains the time domain signal that the sensor are able to retrieve. And in this case, for example, you can see on the right that there is one value which is around 2000, because the tone wood was of low quality in this case, but it was to validate the model, which is more likely to be to explain the delay between the 2 signals, which is a technique borrowed from telecommunication called rake receivers. The idea is to use more sensors to find a shared quantity. The problem is that if we use such sensors, for example, this one that we use costs some euros, but if you have sensors which are not so good, also the estimation can be affected and corrupted by noise. And what we try is to use the state-of-the-art signal processing techniques to find a representation where the noise can be decoupled from the real signal and to delete it. In this way, we can have, starting from this estimation on the upper side, a cleaner estimation on the lower side, where we can see something at least up to 4 kilohertz, which I think is a good news. As Sebastian said, we had the opportunity some weeks ago to measure Strad. I was quite scared because, I mean, if you have to make hammer impacts on a Stradivarius, you have to at least know the value of the violin before doing the measurements. I think I don't want it to know it, and I was more able and calm and quiet to make the measurement. They also brought another violin, and they said that the violin, the copy here, the blue one, these are bridge admittances. They said this violin sounds quite, it is quite the same in terms of sound generated with respect to the Stradivarius. And they say, okay, let's measure the bridge admittance and say something about this similarity. With Sebastian, I've been talking with Sebastian, and we said, okay, we can try to compare the frequency response function, the bridge admittances, but and we can see that up to 1 kilohertz, there is the possibility to say, okay, the resonances are quite the same, so there is some similarity. But it's still difficult and hard to find a way to say, okay, these violins are quite similar, these are not, based on vibrometric descriptors. So the idea was, okay, let's try another representation, and let's take the first 10 resonances inside the bridge admittance. And here you can see 3 violins. So the first one is the copy. The second one is the Stradivarius. And the third one, which I call the reference, is in reality a very low cost 50 euros violin that we have in the lab to make quick tests. And we take for these modes the positioning frequency, the amplitude, and the quality factor. And we tried this kind of genomic representation. And we saw that in this way, we have a signature of the violin that can be used to compute some distance measurements. And we did it. And also we tried to compare them, to compare the distances with other measurements that we did during Cremona Musica last week. The distance was a very normal Euclidean distance, and we get rid of the mean just to have unbiased estimation. And the interesting thing is that if you look, I mean, they're quite incomprehensible if you try to look at specific things, but if you try to look at some possible patterns, you can see that the first two violins seem to be quite different from the other ones. And the last one is the low-cost violin. So the first two violins and the low-cost violins seem to be different from the other ones, and violin 3, 4, 5 seem to be quite similar to the Strad and the copy. So there is a huge green area here, and the green is a low value of the distance with respect to the position of the frequency for each of the 10 modes that we are trying to measure. And also looking at the quality factor, we can see the same trend. So the first two violins are quite different from the others. And talking with luthiers that joined this particular measurement campaign, they say the first two said that they wanted to try something different from the models that they know. They try a lot of things, and they try to be to make their own model. Like the other ones said, we've started from a known model, and we try to make some alteration by our own. So it's quite interesting to see this correspondence between what they said and what these particular descriptors can say. The only interesting thing is that here we have the frequency and we have the Q factor, but we look also at the amplitude and the distances. So here we are comparing each violin in terms of the distance between the amplitude of the 10 modes. And you can see that the overall behavior seems to be very randomic. There's no very trend and a way to say, okay, there are similarities or not. And this is quite interesting because indeed, it was related to the fact that when we make measurements here at the lab, we are quite sure about the position of the peaks and also the width of the peaks, but the amplitude can be affected by several things. For example, the number of measurements that we average for having the bridge admittance, or the particular setup that we use for the measurements. So it's quite interesting to see that the other two are more stable as features, and this one is not. And the idea is to continue this type of study in this type of representation to make the same thing that Sebastian is making with violins, with geometric parameters in violins, because we think it can be very interesting to merge all these perspectives and have a domain which includes all the parameters, and where we can try to measure distances and find a way to map the changes that can be done in the geometry and in the vibrometric domain. So just to conclude this part, signal processing techniques. We use signal processing techniques quite successfully for enhancing the quality of the estimation. We are trying to find some new representation from frequency response function because they contain much information and maybe are not too comprehensible. And the idea is to try with this genetic representation, these distances, and try to see if we can make some sort of clustering or some sort of alternative representation of the vibration data that we have. Thanks for your attention. This is, my talk. And just at last, conclusion of the main conclusion of all the 3 talks. I don't know if you can see the image, if it changes from the presentation to the image, or this is the same screen.
No, cannot see anything. I mean, just the presentation.
Okay, maybe I need to interrupt the sharing and make this. I don't know if you can see the image now.
Yes.
Okay, so I think that the idea of the 3 talks, we talk about very different kind of things, I think. I mean, the approach is the same, the point of view is the same, because we have maybe a tradition which is quite different from the original musical acoustic point of view, but we talk about different types of data, and we think that the future of the lab is to try to merge everything in one compact representation, and one tool which is able to use everything for the sake of violin making. So not to suggest some design choices, but just to map the impact of design choices in violin making inside these 3 particular fields, which are sound field measurements, experimental measurements in terms of vibration, and impact of geometric and material properties inside the design of violin making. That's all.
Okay, thank you. Who would like to ask a question?
I have a question again. Sorry.
Okay, no problem.
Rafael, I have a question about your experimental setup for the near-field acoustic holography. You are measuring in a flat surface over the top plate, and
yeah.
Then you are calculating the velocity distribution in the not plane surface, right?
Yeah, exactly. I mean, I have to, the validation method was like with simulation data, but I can say the experimental setup that will be used then to use experimental data. And I confirm what you said. I mean, the idea is to have a microphone array, a planar microphone array on the upper side of the violin plate. So the idea is to take the higher point of the plate and set the plane in the near field region, and the distance between the plane and the higher points is depends on the distance between the microphones that we use in the grid. So the idea is we take the minor distance between microphones and we use them to set the distance between the microphone array and the plate. And yes, we ignore, I say with some carefulness, the idea that the plate is not planar.
Okay.
Because I mean, neural networks can make this. I mean, it's not important. If you give data and examples, neural networks can understand statistical properties in the data without assuming anything, which is I think the advantage of using this type of techniques. But the problem related to this is, okay, you need the data set, so you need measurements.
So then, in theory, you can calculate now the plane radiation pattern at any distance, no? If you have the distribution of the velocity in the surface. Then,
Yeah,
so
exactly.
in very high frequencies where the wavelength is at the same order of the distance of the valley, it will be important. But in general, you can only say this is plane, and we can calculate planes in every part. Yes, is clear? No? Okay.
Yeah, that's clear. I mean, I think that it's a next step. I mean,
Okay.
the idea is this is near field acoustic holography. So the input that you need in this method is measurement in the near field, so close to the source.
Okay. Okay.
Then the method retrieves the velocity field of the source. So, for example, if you want to make some sound, we can say high fidelity sound radiation simulation, you can use the velocity field that you have retrieved to make again a sound simulation, a radiation simulation with finite element. So you're sure that the velocity field that you're using is characterizing your source exactly, but you are using it to find the sound field generated with finite elements, of course.
Okay.
So the idea of the method is only inverting the sound field that you have.
Okay.
By the way, I mean, you can also, I'm just thinking now out of the box, I mean, you can also use the near field sound field and try to simulate the propagation of this sound field on the outer side, I mean, on the outer direction. But it's a matter of simulation in that case.
Okay, thank you. Thank you. Congratulations.
Raffaele, can I ask a question?
Yep.
Okay. In one of the slides, you compare the similarity between the frequency response functions, Ifrf functions, between like a strata copy and the reference violin. I just wonder, how do you compare the similarity between the frequency response functions? Like you have like a different color. Yeah, you have a different green.
Maybe I can share like again the screen.
Yeah, no problem. Of course.
So the PPT, the slide with like a different green shading, comparing between strata, copy, and the reference.
This one? Should be this one, I think.
The one close to the last one, I think that 3 or 4 before the last one. Yeah, the previous one.
This one?
Yes. Yeah. So how can you compare the Ifrf, the similarity between different Ifrfs?
Yeah, there are. I mean, there are 2 steps. So the idea is, okay, we have the bridge admittances. We find the first 10 peaks of each bridge admittance.
Okay.
Then we can list the 10 modes for each violin. Here is the horizontal, in the horizontal axis, with respect to 3 features, which are the positioning frequency, the quality factor, which is the indication of damping, and the amplitude of the peak.
Okay.
So here you have like a genetic signature of the violin with respect to 3 different features. And I mean, up to now, I think it's still difficult to understand what can be the similarity or not. But for example, you can see that in the first genetic plot here, the mode frequency, the copy and the strad have like the same 3 modes in terms of positioning in frequency.
So you compare both the amplitude and the frequency of the first mode. So, and if they are similar, you give like a, so the lighter color means it's more similar. The more greener means it's more unsimilar, right? So which color, like the higher number means more similar, or the green, Okay, so the green means more similar.
Yeah, in this distance matrices, this is what you're seeing. So if you look at the yellow squares, you are seeing two violins which are quite similar with respect to that feature.
Okay.
So let's take an example. For example, violin 2 is very similar to the low-cost violin in terms of the position of the frequencies.
Okay. But I can see
On
in
the other
this
hand, if
slide, I can see in this slide the scale is from 0 to 2. In the previous slide, the scale is from 500 to 1500. So why they are in different scales? Like
yeah,
in the previous
there's
slides,
a different case because because here the scale is reflecting the particular physical dimension. I mean, here we are same frequency, so we have from 10 Hz to 2 kHz. The mode amplitude is in dB, and the Q factor is in another dimension, less number. But here we are also get rid of the mean, so this is a relative. So, and this can be, 0. This means that 0 is very similar.
Okay.
Equal. Also with respect, we are getting rid of the mean, but the maximum value can be anything because we are not standardizing the standard deviation in this case.
Okay, I think I got the idea of your comparison. And also Sebastian is also explaining in the background in the chat room. So I think that he explained that is a Euclidean distance. Okay, yeah, I think I got the idea. Thanks. Yeah.
Okay, I have the support in the chat, so.
Yeah, I can see the Sebastian is also comments on the chat room.
Yeah, I hear George.
Okay.
If I may ask a question.
Yep.
Does anybody hear me?
Yes, of course, yes, you can.
Sorry, when I do a lot of modal analysis, but I find that I think if I was trying to implement this comparison of the first 10 peaks, it would fall down very quickly because the analysis of an instrument with strings on, with a tailpiece and everything, the analysis is really quite conforms to the sort of textbook description of it. So you have always have some coupling with substructures. There's always some uncertainty about the exact frequency of the mode. If it's split, if you've got a mirrored pair, for example, and also the actual identification of, you have to very, very careful modal multi-degree of freedom curve fitting to have any idea of the accurate information on those things. So I'm surprised that you feel that this actually works or can give really meaningful information. I mean, is this your experience? Do you find, how do you handle a split peak, for example?
Yeah, it's only an intuition because we are trying to do some methods based on data with very few data up to now. The idea is this metric is not enough large to say to be sure that what we are saying is the truth up to now. But the idea is we are trying to explore ways to highlight these differences and these similarities. In my experience, there are a lot of factors changing the results, and indeed it's quite difficult also to read directly estimation like frequency response functions and range admittances because it depends on many things about the setup, about the again, the estimator that you use. So I think it's promising to see some patterns inside. I don't know honestly up to now if this is going to be useful in making a reliable and stable metric for similarity.
A lot of these techniques are used, to me, they're reminiscent of things like mode assurance criterion or frequency response assurance criterion, where you can run the cross correlation between two mode-shaped vectors. So, and that's quite interesting, because if you run two different instruments against each other, you find even if the mode frequencies are shifted, you still see the similarities of patterns matching up.
Yeah, exactly.
But
exactly. Indeed,
it's pointless to run that unless you've got, you've got to have like 60, 70 points per plate before that starts to make any sense.
Yeah, indeed. Yeah, also we saw it during the generation of the dataset for the data-driven model that I showed before, because we tried also different mechanical parameters for the wood. But then you can see that, I mean, in terms of patterns, there's no difference. I mean, the only thing is changing. I mean, that's a simulative scenario. So I'm saying that only in this particular case, but the idea is that for same patterns, you have slightly different eigenfrequencies, because you're shifting with respect to the mechanical parameters of the wood, the position of the peaks inside the frequency response functions and the data.
There's one other thing
so we are trying
me right at the beginning. So I finished that sentence.
Sorry, I
okay.
lost
right,
the last word.
So I thought I felt I was interrupting you while you were still saying something. So I was asking you, would you like to finish that, what it was you were saying? Because I have a separate question.
No, I finished.
Okay.
I finished.
Right at the beginning, you said, well, you couldn't use accelerometers on old instruments because you couldn't glue them, fix them all on the corpus. But nobody does that. You fix the accelerometer, you use the inverse, the reciprocity rule, and you fix the accelerometer, say, on the bridge, and then you use a roving hammer. So, I mean, for work on, particularly with new instruments and instruments of not extreme historic value, this is an extremely practical method.
Yeah, sure. Yeah. I was mentioning more the idea of old violins, because we have the experience of guards inside the museum.
Don't know how many strads and Deljases I've personally measured, or if I include that with other ones that friends of mine have measured on. It's dozens of them. We've never damaged an instrument. But
okay, we will try to convince the museum to make the same measurement, because up to now it's quite difficult to talk with the guards.
Well, obviously you have to use a soft tip on the hammer, so that limits the data to maybe 3 kilohertz. But there again, so does the practical number of points. So it's not, with a roving hammer, it's not practical to measure 500 points on a plate. Like 100 really is as many as it's practical to do. I mean, it's not impossible with aids to place the points, but 70, 80 points on the plate gives you an enormous amount of data.
Yeah, sure.
I finished. Thank you very much.
I think. Okay, thanks for the suggestions. I mean, we try to propose the measurements inside the museum, I think.
Well, if I can help in any way, just get that to me. I can report on previous experience, as it were.
Thanks.
Thank you. But overall, I mean, the stuff you're working on is, your group is very different from the world that I operate in. So I'm looking forward to seeing what, you know, what actually comes out of it, what insights, what uses we can put it to.
Let's see. I mean, I think these are quite interesting results. I personally don't know yet how to like formalize everything and make, because I think that we are in a state that, I mean, the research is very abstract in some sense. So we need to try to make more experimental setups, more practical experiments to see the real issues, I mean, and to try to make these tools more suitable for violin makers and people. I mean, this is my thought.
I mean, the information that you're getting from the directivity studies, it seems to be quite concrete. You know, it's not, it's clear data, but it's still not known to me whether this in any way correlates with the perceived quality of an instrument. You know, is one radiation pattern preferable to another? That is something I'd be interested to know about.
Interrupt there?
Yes.
Well, I mean, we have the good luck that we have instruments that we know that are good. So we can do the correlation between what we already know what's good with the 3D structure and compared to like Chinese 20 euros violin and see what are the differences.
Saying they're good because they're Stradivarius.
Because they are like commonly appreciated as good. I mean, we don't only have the museum instruments, we also have a lot of international players that come here with their own favorite instrument, which, I mean, it's not double blind, but it's being selected by a professional player to be his or her instrument of choice. So I think that gives us a certain standard from which we could infer what are the objective features.
Excuse me, it does worry me a little bit because, as Claudia will tell you, when if you listen to instruments in double-blind conditions, so there's some very nasty shocks that could happen.
Yeah,
so
well,
I wouldn't really think that it's a fantastic instrument because it's played by a great soloist, or because it's a beautiful instrument worth a lot of money in the museum. I mean, that to me isn't a measure of the quality of an instrument. It may correlate, but it's not a measure.
No, it's not a measure. And you remove you say it's not double blind condition, and that's really, you put it double blind, changes completely everything. So.